In Module 6, we are going to look at exponential and logarithmic relations. And before we get into exponential and logarithmic relations, we do have to talk about something called composition and then inverse functions, which is what we're going to start with in section 1. So the first thing I want to review is function notation, which we have seen a little bit in previous modules. So instead of having y equals, function notation is a letter such as f, and then in parentheses x. So f of x equals, and then your equation, you could also commonly see g of x equals, or even h of x equals. Those are very common letters we use from function notation. You can basically use any letter, then parentheses x, and then equals. It means the same thing as y equals. So when we are composing two functions, so a composition of functions, instead of evaluating a function with a number, so we plug in a number for x, what we do is we are evaluating a function with a function. So instead of plugging in a number for x, we're plugging in an equation for x. So our answer when we compose two functions is still going to be a function. So we're still going to have something that contains x. So in our first example, we have that f of x is 3x squared minus 4, and g of x is negative 2x squared. And we want to find f of g of x and g of f of x. So that little symbol right there between the f and the g is the symbol for composition. Another way you can see it is f and then parentheses g of x, which is instead of saying f of x, you're saying I'm plugging in the equation g for x. So what I do is I go through and everywhere I see an x in my equation f, I replace it with my equation for g. So it's 3, and then I replace the x and x squared with negative 2x squared. Then I still have my squared, and then minus 4. So now I want to simplify that equation. So when I square negative 2x squared, negative 2 squared is positive 4. X squared squared is x to the 4th, then minus 4. And then lastly, 3 times 4x to the 4th gives us 12x to the 4th minus 4. And there's nothing else I can do to simplify that, so that is my answer. For g of f of x, another way you can see it is g and then parentheses your f of x. So now I'm going to go through my equation g, and everywhere I see an x, I'm going to replace it with my function f. So I have negative 2, then the x gets replaced with 3x squared minus 4, and then I have my squared. Now this is a little bit different from the previous example. I can't just square what is in my parentheses because of that subtraction sign. So 3x minus 4 squared is 3x minus 4 times 3x minus 4. And what I have to do here is distribute. So it's going to become negative 2 still in front, and then 9x squared minus 12x plus 16. And I have two choices here. I can either combine like terms in the parentheses and then distribute the negative 2, or I can distribute my negative 2 first and then combine like terms. It doesn't matter which one you do. I'm going to go ahead and distribute first. So negative 18x squared plus 24x plus 24x minus 32. So g of f of x equals negative 18x squared plus 48x minus 32. So another thing you can see here is that when I do f of g of x and g of f of x, I may not get the exact same answer. So the order of composition does matter. So it is important you know which one you're plugging into which based on the order of that composition. So our next example, we have f of x is x plus 3, g of x is 2x minus 7. So we'll start with f of g of x. So x gets replaced with the 2x minus 7, which if you want, you can put in parentheses. and then we have our plus 3. There's technically a 1 in front of that x, so it's 1 times 2x minus 7, which is just 2x minus 7, and then plus 3. So for my composition, you combine like terms, and you get 2x minus 4. For g of f of x, we start with the 2. We replace our x with x plus 3. Then we have minus 7. Distributing the 2, you get 2x plus 6 minus 7. And then we will combine like terms, and we get 2x minus 1. So the last thing we're going to talk about kind of goes in line with inverses, and then we'll talk about how to calculate an inverse. So we're going to start with the definition of a function, and a function is an equation representing the relationship between two variables. So there's a lot of different functions out there. You have your linear function, the quadratic function we've talked about our rational function. So a function is just any equation that represents a relationship between two variables. And there is something called a one-to-one function. And a one-to-one function is specifically a function where every x value corresponds to exactly one y value. So some functions can specifically be one-to-one. For example, a linear equation is a one-to-one function because you can never have a repeated y value, whereas a quadratic function is not one-to-one. Because in a quadratic, because it does have that parabola shape, every y value, except where the vertex is repeated. So one way you can tell whether or not a function is one-to-one is something called the horizontal line test. So it is used to determine if a function is one-to-one. So it's very similar to the vertical line test, which tests to see if something is a function. So if it passes the vertical line test, it is a function. If it fails, it's not. Horizontal line test works the exact same way. If something passes the horizontal line test, then it is a one-to-one function, and if it fails, then it's not. So I'm going to use the examples I just talked about. So a linear equation, so if I just have a line, if I draw an infinite number of horizontal lines through that equation, it will only ever touch in one place. So this is an example of something that is one-to-one. Whereas if I draw a quadratic, so my U shape, and I draw horizontal lines, they are going to touch in multiple places. And it doesn't have to be that the horizontal line always touches in more than one place. It's that if any horizontal line touches it in more than one place, it's automatically not one-to-one. So this one is not one-to-one. So the way you can determine whether or not a function is one-to-one is based on the graphs, is you're going to use Desmos. So I'm just going to draw a sketch of what these look like in Desmos. So for this first graph, y equals x to the fifth. Very rough sketch of what it looks like if you graph it in Desmos. If I were to draw horizontal lines through that graph, it would only touch the graph in one place. So this function is one-to-one. My second example, we have g of x equals 9x to the 6th minus 7x to the 5th minus 4. Again, I'm just going to do a sketch of what this looks like in Desmos. So roughly kind of like a W. Yeah, roughly that's what it looks like. So if I draw even just one horizontal line, it's going to touch in more than one place. So this function is not one-to-one. So now let's talk about what an inverse is. So in an inverse function, when you plug in a value in a regular function, so if I have my function f of x equals 3x minus 11, I plug in a value for x, I get out a value for y. The inverse function says if I plug in a known y value into my equation, I will get out its corresponding x value in the original. So if I know f of 2 equals negative 5 in that equation, then what value for the inverse of x do we know? So that notation there, the f with the negative 1, is called inverse notation. So what an inverse does is it just switches x and y. So if I have the point 2, negative 5 on f of x, which is what f of 2 equals negative 5 means, that means on the inverse function, I have the point negative 5, 2. So you're just switching x and y. You're not changing any signs, you're just switching x and y. So there are two ways to check whether or not two functions are inverses of each other. There's an algebraic way and a graphical way. And we are going to use the algebraic way because it's hard to tell from the graphical way. So the algebraic way is if f of g of x equals x and g of f of x equals x. So the one time you actually want your two compositions to be equal is if you're verifying if they're inverses. And it's not just that they're equal, it's that they both equal x. So you perform both compositions, and if both compositions equal x, then those two functions are inverses of each other. If you're looking at their graphs, you look to see that one of the graphs is reflected across the line y equals x, which ties directly into the algebraic way, because if they both simplify to x, that's basically the equation y equals x. It is hard to tell specifically from a graph if something is reflected across y equals x, which is why we don't typically use the graphical method to determine if two functions are inverses. What we do is we use the algebraic method. So that's what we're going to do in our next example, is we're going to verify that the functions f of x equals 3x plus 4 and g of x equals 1/3 x minus 4/3 are inverses. So I'm going to start with calculating f of g of x. So we're going to have 3, and then in parentheses, I'm going to put my equation g, 1/3 x minus 4/3, and then plus 4. I'm going to distribute my 3 into my parentheses. So 3 times 1/3 is just 1. So I'm left with x minus 3 times 4/3 is 4 plus 4, which gives me x. So far so good. My first composition has equaled x. I still have to check the second composition. I can't just stop here and say, yeah, f of g of x was x. So they're inverses. You must check g of f of x as well. So g of f of x, we start with the 1/3, and then in parentheses, we'll put 3x plus 4, and then minus 4/3. So I'm going to distribute my 1/3 in my parentheses. 1/3 times 3 is going to be 1, so I'm left with x. 1/3 times 4 is 4/3, and then I still have my minus 4/3. And positive 4/3 minus 4/3 It's going to cancel, so we get x. So yes, they are inverses of each other. Now, if I had done f of g of x and I didn't get x as my answer, I don't have to check g of f of x. I can stop right there and say, no, the functions are not inverses. Because if one of them doesn't equal x, it doesn't matter if the other one does. So now that we've talked about how to check if two given functions are inverses, we want to talk about how do you actually find an inverse equation. And it's 3 steps. So the first step is to set your equation equal to y. So we don't actually use function notation to find an inverse. We use y equals. So no matter what function notation you're using, you'll always rewrite it as y equals. And then as we've previously discussed, an inverse just switches x and y. So your second step is to then switch x and y in your equation. Technically speaking, that is the end of finding an inverse because that's what an inverse does. However, you now have an equation of the form x equals instead of y equals. And we don't read equations as x equals. So our third step is now to resolve for y. So we can get it back in y equals format. And then our fourth step is to write our answer using inverse notation. We don't want to leave it as y equals. We do want to write our final answer using inverse notation. So for example, we have f of x equals negative 2x minus 7. So my first step, write it as y equals. So y equals negative 2x minus 7. When I switch x and y, I do not move any coefficients of x. I'm literally just switching where x and y are. So it becomes x equals negative 2y minus 7. Now I'm going to resolve for y. So my first step is going to be to add 7 to both sides. So we get x plus 7 equals negative 2y. And then we're going to divide everything by negative 2. Now, I don't like to write fractions where you have a negative in the denominator because I now have y equals x plus 7 all over negative 2. And I don't really like to leave negatives in the denominator. So when I write this in inverse notation, I'm going to have my f with my negative 1 of x equals, and then I'm going to go ahead and split this up into 2 fractions. So x over negative 2 becomes negative 1/2 x. 7 divided by negative 2 becomes minus 7/2. And that's my inverse notation, and that is the inverse of the function f of x equals negative 2x minus 7. If you wanted to leave it as a fraction, you could have left it in that format by doing f inverse of x equals negative x minus 7 all over 2. All I did here was I moved my negative to the numerator so that I wasn't dividing by a negative. Both of these are correct answers and would be acceptable on an assignment or a quiz. Let me know if you have any questions about what is a composition of functions, how to find a composition, and then how to find an inverse.